Alright, this video is going to be on acceleration. Hopefully you remember that acceleration is merely a change, or rate of change of velocity. So it tells us how fast or slow velocity is actually changing. Acceleration is actually the velocity, the final velocity minus the initial velocity over the time. How long did it take for the velocity to change? When we look at the variables for this equation, we use a for acceleration and v, f for final velocity, and this v0 is pronounced v naught, is the initial velocity over time, so divided by time. Or you could see it as acceleration is equal to the final velocity, vf, minus vi for initial velocity divided by time. Or you could see this as acceleration is equal to this weird triangle thing. Is actually Greek letter delta, and it represents change. So this would be the change in velocity over time. So all of these equations are the exact same equation for acceleration. One other thing is acceleration can be positive or negative. A lot of people sometimes say deceleration for a negative acceleration, but keep in mind, since acceleration is dealing with velocity, that means we have vectors come into play, and so the direction comes into play here. For our first example, I'm going to go through this one with you. A skateboarder has an initial velocity of 3 meters per second and comes to a stop in 2 seconds. What is the skateboarder's acceleration? So what I'm going to do is I'm going to actually go through and figure out what information are we given. Initial velocity of 3 meters per second. We come to a stop, and it takes us 2 seconds to do so. What are we looking for? We're looking for acceleration. So I think back to all the equations I know, and I'm like, hey, I just went over one. Acceleration is equal to the final velocity minus the initial velocity divided by time. I have all those things. And luckily, I'm looking for acceleration, and the a just happens to be by itself, so I don't need to worry about rearranging any equations. All I need to do is plug in my numbers. My initial velocity is 3 meters per second, so I'm going to put that where vi was. My final velocity, vf, is 0 because I come to a stop. No longer moving, so I'm not going to have a velocity. And it took 2 seconds to do that. Notice that the top part is in parentheses, which means I got to do that first. So I'm going to have negative 3 divided by 2, and simple math right there. My acceleration was negative 1.5 meters per second squared. The unit for acceleration is meters per second squared, since it represents the change in velocity, how long it takes for that change to occur, and velocity is measured in meters per second. Okay, example 2, I want you guys to try on your own. So go ahead and pause this video. Yes, pause it for real. Give yourself time to go through what are you given, set up your equations, and try to figure out how to solve this problem. Did you pause the video? For real though, pause it. Work it out. Alright, hopefully you actually attempted this problem, because the acceleration is 4 meters per second squared. So if you're not sure how to get that, or that you didn't get that, please ask for help. Example 3. A cyclist starts at rest and accelerates at 0.5 meters per second squared for 20 seconds. What is the cyclist's final velocity? Alright, so we're going to go through. What are we given? We start at rest. That means we're starting with nothing happening. So we have no velocity. We accelerate at 0.5 meters per second squared for 20 seconds. What are we looking for? We're looking for the final velocity. So I'm going to set up the equation that I know. Acceleration, final velocity minus initial velocity, divided by time. But crap, this time I'm looking for the final velocity. That means I need to rearrange the equation so I have vf by itself. Since I'm dividing by t here, I'm going to get rid of that first. So dividing by t, that means I need to do the opposite, which is multiplying by t, both sides. So I'm going to have AT is equal to VF minus VI. Still need to get VF by itself, so I need to get rid of this VI. Since I'm subtracting VI, I'm going to need to add VI to both sides. So I'll have AT plus VI equals VF. And VF is now by itself, so I just plug in the rest of the numbers. 0.5 for the acceleration, 20 for the time, 0 because I started at rest, and that's going to all equal my final velocity, which is 10 meters per second. Example 4, I do want you to try on your own, but I will give you a hint that since it is dropped, the ball, whatever ball, since the ball is dropped, the initial velocity is going to be 0. So pause the video, give yourself some time, work it out. Hopefully, you got 5 seconds, and if you did not, please ask for help. Alright, last little bit I want you guys to look at is this graph. This is a velocity time graph. Very similar looking to the graphs we had looked at previously in the position time graphs, but the difference is instead of position here, we actually have velocity. Okay, so we actually have a speed here. So what I want you to remember is when we're talking about graphs and we look at the different slopes of graph, slope is rise over run. So our rise is velocity, our run is time. So we have velocity over time, which is acceleration. So whenever you have a slope, you have acceleration occurring. So now we need to think of, well, what's happening here when there is no slope? Does that mean the object or the person is stopped? No, because this right here is at 60 meters per minute. That means this object or person is moving 60 meters per minute at a constant rate for, in this case, 10 to 15, for 5 minutes. So when you have a flat parts of velocity time graph like this, that's a constant speed or a constant velocity. There's some negative acceleration going on and then some more positive acceleration. Well, hopefully this helped as an introductory video for acceleration.